We're now ready to pick up where we left off. Last time I talked about some of the generic capabilities of Java synchronizers, things like mutual exclusion and coordination and atomicity, and also barrier synchronizers and so on. Now we're actually going to talk about some of the Java synchronizer classes in a bit more detail. We will, of course, go through these things in much more detail later as we go through the classes one at a time, but I want to give you the bird's eye view so at this point so you have the big picture perspective. So the bulk of the synchronizers in Java are in java.util.concurrent and java.util.concurrent.locks, and there's a whole bunch of them. You can see here's the package summaries for these different classes. So take a look at that stuff if you want to get the overall view. Here are the ones we're going to be focusing on in this class, which is not all the synchronizers in Java, but it's the ones that are the most common. And so we're going to be showing the features and classes, how they're implemented, how they're used in Java and in practice. So we're going to show how it's implemented. The various synchronizers are implemented in Java, so you'll see how they work under the hood. And then, of course, perhaps even more usefully, you'll know how to use them in practice, right? Knowing how they're implemented is cool, but it's most cool when you see how they get used. These synchronizers are used all over the place. They are used in applications, of course, like the ones you'll be writing. They're also used in a lot of the class libraries, both the ones that are kind of at the infrastructure level and the ones that are closer towards the application frameworks level. This stuff is very, very common. One of the most basic synchronizers, which you'll get a chance to play around with a couple different ways in this class, is called a Reentrant Lock. And this is a mutual exclusion lock that extends and enhances the built-in monitor lock capabilities. What does it mean to be reentrant? It's a funny term. Sometimes it's known as recursive. But reentrant means that the thread that holds the lock can reacquire it without deadlocking on itself. That's what reentrant means. And so you'll get a chance to, those of you, especially those of you taking the class for graduate credit, will get a chance to play around with this because you get to implement a reentrant lock. Another characteristic of a reentrant lock is that a reentrant lock must be fully bracketed. And what that means is the thread that acquires the lock must be the one to release it. There's some synchronizers, like semaphores we'll talk about later, that do not have this fully bracketed property. But reentrant locks are fully bracketed. And you'll get a chance to see that. And you'll use them in that form in our code. Another variant of reentrant lock is called Reentrant ReadWrite Lock. And this was designed originally back in the day, back in Java 5, when the concurrent synchronizers were introduced in earnest into Java. It was intended to improve performance when a resource or resources are read far more often than they're written to. So a good example would be the undergrad catalog at Vanderbilt, which changes once a year. So it's read a lot by people who want to see what the catalog is, but it's very rarely written to, in other words, updated once a year. So a reentrant lock, a reentrant read-write lock, allows multiple threads to read from the resource concurrently. Oh, I should also have mentioned that a reentrant lock, the analogy, I like to give human known uses for everything. So for a reentrant lock, the human known use is the restroom protocol in an airplane, where you have two states, vacant and occupied. And when you can't go in until it says vacant, and once you're in, you shut the door and you lock it and it becomes occupied, and at that point, no one else can come in. And when you leave, you, the thread, are the one who releases the lock. So that's what it means to be fully bracketed. Sorry, I forgot to explain that. Reentrant read-write, so reentrant lock is very common, very useful. Reentrant read-write lock has a lot of features which are both a blessing and a curse. And I won't talk about all these features in detail now, but it turns out that it's actually not very efficient. Because of that, because of the inefficiency of reentrant read-write lock, later versions of Java 8, introduced something called a stamped lock. And a stamped lock is also a reader's writer lock, meaning that there can be multiple readers, but only one writer at a time. That's more efficient than a reentrant read-write lock. And it's really, really cool. And we will have a chance to look at its implementation when we get further in the course. So it has the same common properties of a reentrant read-write lock in that you can have multiple readers and single writers, but it's a lot more efficient. And one of the other things it does is it supports optimistic reads. And we'll talk more about what an optimistic read is when the time arrives. But an optimistic read assumes there is no contention for a resource. And therefore, in that case, when there is no contention, it's super duper duper fast. There's really literally no locking overhead at all. Another feature that a stamp lock supports that is unique relative to a Reentrant read-write lock is lock upgrading. So you can upgrade the lock from a read lock to a write lock efficiently. The next topic is a very fascinating one. The next synchronizer we're going to cover briefly is called a semaphore. And this has been around for a very long time. It maintains things called permits that control thread access to a limited number of shared resources. You will get lots of experience using semaphores in this class because that's the heart and soul of our Palantiri Manager portion of the assignment, which is the one that's due next, 1B, which I've also released the video describing what that assignment's about on the web. So basically, just like with the Palantiri Manager, where you have a certain number of Palantiri, let's say you have 4 Palantiri you can gaze into. You want to make sure you don't have more than 4 beings gazing into that set of Palantiri at the same time. A good human-known use of a semaphore is the protocol used to play beach volleyball. So when I was a graduate student at the University of California, Irvine, right by the water, go down to Corona del Mar Beach. This is a picture of it, and they had a whole bunch of volleyball courts because everybody goes and plays beach volleyball because it's not 25 degrees out in February or January like it is here. So the protocol was they had a bag full of beach volleyballs, 1 ball for every court. And so if you wanted to play beach volleyball, you sent a representative from the teams that wanted to play. If there was a ball in the bag, you could take the ball, go find a court and play. And when you were done, you would put the ball back in the bag. If there was no ball in the bag, that meant all the courts were in use, and then you had to wait for someone to put a ball back in the bag. So that's an example of a semaphore. It does more things than that, but it basically allows you to control access to a limited number of shared resources. In this case, a shared resource would be the volleyball courts, right? The operations on a semaphore, unlike things like stamp lock and Reentrant read-write lock and Reentrant lock, need not be fully bracketed. So the thread that acquires the semaphore need not be the one to release it. And we'll take a look at that later when we talk about our ping pong example, where 2 threads take turns pinging and ponging in alternate order. The next topic is condition object. Next synchronizer is condition object. This is a really interesting synchronizer. And what it does is it allows a thread to wait until some condition becomes true. And this is quite different than what we talked about earlier with Reentrant lock and stamp lock and Reentrant read-write lock. Those locks make other threads wait until the thread that owns the lock is done. So it's basically a way of keeping other threads at bay while you do your thing. Think about the restroom analogy we were talking about before, right? You're doing your thing. You don't want anybody to interrupt you. Condition objects are kind of the reverse of that. It's a way for a thread to put itself to sleep until some condition becomes true. So you put yourself at bay until you can make forward progress. And the human known use, which I always love here, is pizza delivery. So imagine that you're a student, but you want to go work a part-time job to make some extra money. And so you decide, because everybody, who doesn't like pizza? It's always a good business. When times are good, people eat pizza. When times are bad, people eat pizza. There's always going to be demand for pizza, right? So imagine you go with some of your friends to the pizza delivery place like Papa John's or Domino's or whatever. And that's going to be your second job. But you're tired because you're a student. So when you're not actually delivering the pizzas, you're going to sleep, right? You're going to take some rest. And in order to deliver a pizza, you need 2 things. You need a pie, right? You need a pizza pie, and you need the keys to the pizza delivery vehicle. And so when a pizza becomes available, the cook rings a bell, and that wakes you up. And then you go and you say, can I get the pizza? Can I get the keys? But remember, your friends also are working with you. So whoever gets there first might get the pizza, might get the keys. And therefore, if you don't get the pizza or the keys because someone else has already grabbed them, you put yourself back to sleep because you need to catch up on some rest until either the keys show up again when someone comes back from delivering the pizza, or when the cook puts another pizza out for the cook from being put in the oven. So the point is that when you're not able to make forward progress, you put yourself to sleep, and then you get awakened and notified, and you see if you can get access to the resources you need to continue. Condition objects are always, always, always used in conjunction with a reentrant lock. And you'll see reentrant lock actually has a factory method called new condition that makes a condition that's associated with it, and therefore it allows you to be able to coordinate access to the shared resources atomically. We'll talk a lot more about that later. I don't expect you to understand that in detail now unless you are a condition object savant and already understand all these things. We're now going to transition into several different barrier synchronizers. There's 3 of them in Java that are important for our purposes. The first one is very simple. It's called countdown latch, and it allows one or more threads to wait on the completion of operations in other threads. And there's a bunch of analogies here I like to use. One is what we might call an entry barrier, which says, don't start the horse race until all the horses are in their stalls, right? You don't want to give somebody an advantage because they get there first. And there's all kinds of other barriers too, like exit barriers. And so we'll talk a bit about like a museum guide, giving a guided tour through a museum and rooms in a museum in a second as another example of this. So countdown latch, very simple. It allows threads to wait on something. And so when something completes, then the threads can start to do their thing. There's another variant of synchronizer, barrier synchronizer, called a cyclic barrier. And it allows a set of threads to all wait for each other to reach a common barrier point. And a good example, I'm always looking for human known uses. Horse race is okay, but probably a better example would be an assembly line. Like if you're familiar with the Model T Ford, made the people want to get up and go. And so what you could do with a Model T Ford is you'd have teams of workers along an assembly line. And each team would do some specific thing. Someone would put the tires on, someone would put the engine in, someone would put upholstery on the seats or whatever, right? And you would have an assembly line and the stuff would come through, and when the car got to your team's station, imagine a little light would go off, and then that team would cluster around and do their thing. And then when they're done, they step back and the car moves down to the next slot in the assembly line. And so a cyclic barrier allows a set of threads, in this case, a set of workers, to wait for each other to reach a common barrier point, like next car is ready. So there's cyclic barrier. And then the last barrier synchronizer we're going to talk about is called a phaser. Kind of like I always think of Star Trek phasers, but it's not really like that at all. Phaser is a more flexible, reusable, and dynamic barrier synchronizer that subsumes cyclic barrier and countdown latch. In the sense that you can do everything you can do with cyclic barrier and countdown latch with a phaser and then some. Now, you might ask, why do they have the other stuff? Well, phaser came later, for one thing, but phaser is also a bit more complicated to use, as we'll see. So here's a way to think about the phaser. It's a little bit different in some ways. Think about constructing a house. When you build a house, there's a bunch of different things that need to be done by different crews. So you have the framers. You have the people who are going to put on the bricks on the outside. You have the roofers. You have the electricians. You have the people who put up the sheetrock to make the walls, blah, 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 lots of different things. And each of those different teams may have different numbers of people. So it's not like a cyclic barrier where you have the same number of people each time. Here you might have, 7 roofers, 3 framers, 5 electricians, whatever. I'm probably making those numbers wrong. But the point is that different phases require different numbers of people to work on stuff. And so the phaser gives you the ability to coordinate different groups of things over different periods of time. So that's the end of our overview of Java synchronizer classes. You will get lots more exposure to all of these things, or almost all these things, by the time we're done in the class. But this is just the bird's eye view, the forest view rather than the tree view, which we'll get later.